Welcome to Insight xtUML, a learning series. In Episode 3, I began a discussion on creating an xtUML model. Here, in Episode 4, the focus will be on the steps required to implement activity inside the model. At the conclusion of this episode, all the pieces necessary for an executable model will be in place. Before I begin, I would like to thank the xtUML community for organizing this series and for providing the opportunity to share with you some of my knowledge of xtUML. If you are unfamiliar with xtUML.org, I encourage you to visit the site. This is a community of like-minded members that are actively working with xtUML and are willing to share their experience. As a community member, I benefit from the experience of others and the ongoing development of tools that the xtUML.org community is involved with. As part of the community's effort to broaden the awareness of xtUML, this series, called Insight xtUML, a learning series, was started. These seminars are prepared and presented by community members to share their knowledge and experience with others. I want to remind everybody that these events are recorded and can be viewed by visiting the xtUML channel on YouTube. In Episode 3, the steps of the xtUML process were introduced and then the analysis step performed. For those that missed that episode, I have included a brief review in today's presentation. Following that, I will dig deeper into the second step of the process, the component design step. As we progress through the discussion, I will touch on the role of data modeling in component design and then review how class diagrams, state diagrams, and action language are used in the construction of an executable model. At the conclusion of the design step, a complete xtUML model will be ready for execution inside a simulation environment. A full exploration of validation and verification will be discussed in a separate episode in this series. Throughout the discussion, I will refer to the example of modeling a running watch as a case study to illustrate the ideas presented. In Episode 3, the steps of the xtUML process were introduced. For those that missed that presentation, this section will provide a short overview of the steps. Then, in the remainder of the discussion, the component design step will be explored in detail. Beginning with requirements, the first step in the process is analysis, and this step is typically performed by systems engineers. Here, requirements are collected into related groups, and a structural specification is produced. These specifications become the starting point for the second step, component design. Components and their behavior are expressed in terms of data members, lifelines containing the control and processing evolution of each data element, and their relationship to other domain members. These component models are executable. So in Step 3, test engineers connect system components to test components and then execute the combined system. The captured results for each test provide the artifacts needed to document validation and verification testing. The final step is implementation, and this work is performed by integration engineers. During this step, the xtUML model is translated from the platform-independent diagrams into a platform-specific representation. In this form, the realized component can then be integrated with other components to form the final realized product. Ideally, a project requires only one pass through this process to get from requirements to implementation. However, my experience has been quite different, and that new requirements or new details uncovered during design will lead to iterations. These surprises are a common aspect of today's systems design experience, and the xtUML approach accommodates them very well. Now, let's look at how the xtUML process accommodates these iterations. In the analysis step, system engineers are organizing requirements in an effort to identify the structure of the system and to document the communication between the domains of the system. This is work that progresses until new requirements no longer lead to modifications of either the structure or the communications interfaces. It is at this point that Step 2 is able to proceed. In my experience, this transition occurs well before all the requirements have been fully analyzed. So even though Step 2 has begun, I often see the work of analysis continuing in parallel. The design step is about enhancing the structure produced in Step 1 by modeling the behavior inside each domain. Since domains are intended to be autonomous, they are ideal candidates for parallel development or continuous design practices. In each of these independent paths, there is the opportunity to stagger the addition of new behaviors and to flow into the third step, execution, models that are incrementally matured. Also, I often find that as the detail inside a domain model increases, it leads to opportunities where further analysis should be performed. And in the xtUML process, this additional analysis can be performed without delaying the efforts on unaffected components. Even though xtUML models are constructed from diagrams and actions, these models are executable. In Step 3, we exploit this characteristic to validate the current interpretation of the requirements provided by analysis, and remove many of the bugs that might have crept in during design. In this step, it may be necessary to create specialized test components, and xtUML is sufficient to model these components as well. Once test engineering has completed running their tests and produced the reports they need to demonstrate that a component satisfies the requirements, then Step 4 is ready to begin. As with the design step, if bugs are identified in testing, then sending the component back to an earlier step is naturally accommodated by the process. The fourth and final step of the xtUML process is the translation of platform-independent models into a platform-specific implementation. This translation is performed by a model compiler that is constructed to be aware of the attributes of the target platform. The translation produces the implementation artifacts, everything that is needed to integrate and assemble the final product. As part of this activity, system-level testing should be performed, and co-simulating implementations in the same system context is a strong final check. For the remainder of the presentation, I will concentrate on the steps involved in performing component design. As I progress through the discussion, I would like to continue to use the example of a runner's watch, which was featured in Episode 3 to demonstrate the concepts discussed. If you're not familiar with these devices, this is a watch that runners use to monitor their fitness while training. It tracks a runner's location, often using the GPS navigation satellites, monitors their pulse rate, and periodically stores this data until it can be downloaded onto a computer for further analysis. In Episode 3, the analysis model was constructed for the runner's watch. As part of this model, a structural description containing component diagrams and interface definitions was assembled. To help identify the structure and document the allocation of behaviors to the various components, use case, sequence, communication, and activity diagrams were also produced. Once the analysis model is completed, it is the role of designers to implement the behavioral description inside each component according to this allocation. At the conclusion of Episode 3, the analysis of the runner's watch led to the structural diagram shown here. The selected structure included a location component, a user interface component, a heart rate monitor, and a tracking component. With this structure, each component was found to be autonomous, with a cohesive collection of services. Also, the message exchange between components were concentrated in a small number of ports with simple interface definitions. In general, high-quality analysis models will share these characteristics of cohesion and concentration. Here are the interface definitions for the proposed model structure. Since the proposed structure has allocated related behaviors and high-frequency messages to the same component, the requirements for inter-component communication become very compact, with few interface definitions being required. Note that the definitions are organized into services and notification-oriented messages. It is from this starting point that the design step begins. Analysis provides a map of what action is performed where, and in design we answer the question of how each action is achieved. To describe the activities within a component involves 3 layers of detail. At the outer level are class diagrams, which show data members of each class, operations to be performed on the data member, and associations between the classes. Next, inside each class, functional or data processing details are expressed in state machine diagrams and functions. Then, at the most detailed layer are blocks of action language that describe the procedural steps that must be performed by the function, operation, or state within the state machine. Once all 3 layers have been completed, then a behavior can be considered implemented. So the first step in design is to construct a class diagram that documents the class members and the associations between classes in the system. This work is typically performed on a component-by-component basis, and most often will progress in parallel. On a class diagram, you will find that each class member is represented by a box containing a class name and a list of attributes, which are the pieces of data necessary to describe an instance of the class. When picking a class name, I find that using a common name combined with descriptive adjectives provide the best combination of precision and general understanding. Between classes are association lines that include verb phrases, association labels, and multiplicity conditionality indicators. Verb phrases are an important part of the vocabulary of a diagram and contribute to the comprehension of the diagram. The verb phrase should be read in the form Class A, verb phrase opposite Class A, Class B. In the example shown, a waypoint starts a route, while a route begins with a waypoint. Association labels are used for navigation across relationships that connect instances of classes together. The multiplicity of an association between 2 classes is defined by the number of class instances that participate with each other. Conditionality speaks to whether one class of the association can exist without the other side also existing. In this example, we find a waypoint can exist and not be the start of a route. For the current example, the first waypoint is related to a route across association R1 and R2, while the rest are related across only R1. Given those elements, the first activity in defining the class diagram is to identify a collection of objects that are involved in the behaviors of the component. Characteristics of these objects, which might be required as part of the functionality or data processing, are then recorded as class attributes. between some pairs of objects, there are likely to be relationships. Note these real-world connections between objects as associations between the related classes on the diagram. As the class diagram matures, the identified class, attributes, and associations become a vocabulary for describing the activities of the component. A useful test of the quality of your class diagram is to pick an activity from the component's allocated behavior and write a description using the vocabulary of the class diagram. This exercise can often uncover areas where additional attributes or discovered attributes should be added to the class, or where redundant attributes exist. When defining the classes within a component, I have found the brainstorming exercise called a class splits to be a productive approach. During this exercise, a list of candidate classes inspired by system roles, physical objects, events or interactions that cause something to happen, or shared characteristics are collected. There are no wrong answers at this point in the development. Once the exercise is completed, there are often overlapping classes, so the next step is to remove and redefine classes until a minimum consistent set is identified. Associations are formal relationships between classes, and they provide a mechanism to locate information elsewhere in the model. On the class diagram, associations are represented by the lines between related classes. In some cases, the relationship is between instances of the same class, and these relationships are called reflexive associations. Also, these relationships are always between two participating classes and are bidirectional. To describe the number of instances at each end of the relationship, the multiplicity and conditionality of the association are used. By permitting each end of the association to have 0, 1, or many instances, a complete vocabulary for the relationship is provided. I am sometimes asked why only these three cases are considered, even when the upper bound of a relation's multiplicity is known. It's important to recognize that in that circumstance, the upper bound is actually a platform-specific detail, and its inclusion in the model would reduce platform independence. So by considering only the 0, 1, or many case, the constructed class model is more likely to be platform independent and better suited for model compilation and potential reuse later on. An association is reflexive when each end of the relationship is an instance of the same class. A common example of a reflexive association is a list of items, and since a list has a beginning and an end, the association is generally found to be conditional with multiplicity of 1. Navigating such a relationship can be challenging, and the key is to use the verb phrase to distinguish direction. Association classes are used to contain attributes that hold data that isn't properly part of either of the participating classes. These association classes often appear when the participating classes are linked by multiple occurrences of the relationship, and it is the associated class that contains the information that uniquely identifies each occurrence. An associative class is denoted by a dashed line drawn from another relationship line. Instances of an association class come into existence when the relationship is created. Later, when the participating classes are unrelated, the associated class is also destroyed. The generalization relationship contains properties that are similar to inheritance. It allows the modeler to select attributes common to subclasses and put this data into a superclass. It also permits the combined supertype-subtype to specialize the class behavior. For each instance of a supertype, there coexists an instance of a subtype. So the relationship is essentially a one-to-one conditional relationship. Also, this relationship does not require a verb phrase, since the association can always be described using the phrase is-a. For the example shown, the class model indicates the step goal class is a supertype, while classes pace and pulse are subtypes, and that their relationship can be described by the sentences pulse is a step goal and pace is a step goal. There is no descriptive statement for the other direction. To construct quality class diagrams, it's important to create meaningful names for the classes and descriptive phrases for the associations. As mentioned earlier, it's helpful to test your class diagram by writing descriptions using the vocabulary of the diagram. Also, as you construct these descriptions, consider whether the relationship always holds and whether more than one participant class can occupy the relationship. In this way, you will test whether the current conditionality and multiplicity for the relationship is complete. Attributes are the final pieces that complete the description of a class. They are the shared characteristics of all instances of a class, and which characteristics are relevant depends on the purpose of the model. In general, only attributes that are involved in the actions or control of a class should remain as part of the class diagram. To further improve the quality of the attributes, I have found the following recommendations to be helpful. First, all attributes should be atomic, rather than a combination of attributes. Secondly, each instance of a class should require all attributes to be given a meaningful value. Lastly, each attribute should relate to the entire class and not just a portion. Applying the described steps to the example of the runner's watch gives 4 class diagrams, 1 for each component. Now the primary data processing component is the tracking component, and here we have the associated class diagram. The role of the tracking component is to store the details of a workout and to provide processing services to the user interface component. So looking at the class diagram, we find that the TrackLog class has been allocated the role of managing data collection and responding to processing requests from the user interface. Also, it appears that the location of each point on the route is stored in a track point, and that this information is organized through a reflexive relationship. In contrast, for the processing of lap times and heart rate statistics, only aggregate results will be provided, since the lap marker and heart rate samples are related through a simple one-to-many association. Having captured the data structure of the executable model, the next step is to model the dynamic behavior of each class. Once the class diagram has stabilized, the next layer of detail to be added is dynamic behavior. For those classes that progress through stages during their lifetime, xtUML uses state machines to model this life cycle and state events to trigger progress. In an xtUML model, the state of the component is distributed across the state machines within the class instances that exist at that moment. For a particular state machine, state transitions are driven by events received by that instance, and events can originate with activity from within the instance, from related instances, or from port messages received from other components. State machines are captured using state diagrams, and the elements of every state machine are states containing activities, transitions that connect adjacent states, and events which trigger a change of state across the assigned transition. The steps to construct a state machine, that matches the lifecycle of a class instance are very basic. To start the process, begin by drawing all the known states. In each state, write a small description of the activity that occurs within this state. Next, connect some of the states using transitions that are known. If there are unused known transitions, then consider adding a discovered state. Now check for completeness, and if gaps are uncovered, define events, discovered states, and discovered transitions until a complete state machine is constructed. In the runner's watch, the user interface component contains a state machine to manage the display information in the various display modes. This state machine contains all the elements and is representative of the typical xtUML state diagram. The third and lowest level of detail in an xtUML model is the specification of activity within state machines, functions, and data processing. To define these actions, the Object Action Language, or simply OAL, is used. OAL is the syntax that xtUML uses to interact with other elements of the model, to create instances of classes, to assign values to variables, to generate events to state machines, and more. By design, OAL is meant to be a natural syntax intended to aid in comprehension, and while in many areas there are analogs to conventional programming languages, OAL is intended to remain abstract and to not prescribe implementation specifics. Consequently, OAL offers a set of operations that is exactly the minimum needed to complete the description of how the component should work without committing to a specific implementation or platform. It contains a means to manipulate instances, navigate associations, perform computation on attributes, and advance the state of the system through events and messages. In this portion of the presentation, it is not my intention to teach you OAL. Instead, by quickly reviewing the building blocks of the language, I intend to give you a sense of the balance between abstraction and computational detail that can be achieved by using OAL without introducing platform specifics. Beginning with storage variables, OAL includes a rich collection of data types that permit flexibility in modeling. It also uses implicit typing for transient values computed during an activity. Calculations are supported through expressions that are assembled from a set of basic operators. Actions can include local conditional and priority decisions using if statements and a combination of else or else-if clauses. And for repetitive actions, OAL offers for each and while loop constructs to describe these activities. To organize common computation and to enhance comprehension, OAL offers parameterized function calls. The xtUML approach to modeling using component diagrams and class models is intrinsically object-oriented. As a result, OAL must offer a means to create and delete instances within a component. As well, before any actions within the class can be executed, or any relationships used, there must first be an instance of the class itself. Once instances are created, associated relationships between these instances are not instantiated at the same time. An explicit relate statement is required to complete the connection. Once instances are created and associations established, specific instances or groups of instances are identified using the select statement. In this example, the keyword any is used to modify the selection, such that any random instance is picked from the set of available heart rate monitors. A more precise selection from a group of instances can be achieved by performing a select many operation, and then refining the search using the where clause. During the discussion of state machines, I mentioned that a change of state can be initiated either from within a component by generating an event, or externally by the arrival of an interface message. Each of these actions is initiated by OAL. For events that are destined to state machines within the component, the generate statement is used, while the send statement is used when the destination state machine is located in another component. To summarize, xtUML component design is about creating executable behaviors for the components identified during analysis by adding classes, state machines, and activities to the component diagram. With this combination of diagrams, an xtUML simulation environment can perform the third step of the process, validation. In that environment, the runner's watch is likely to perform similar to this model. It is challenging to fully explore a topic like this in just 30 minutes. If you are interested in learning more about the ideas presented here, I encourage you to consider these two books. They offer a good balance of instructional material for those new to xtUML and of reference material for the expert. This concludes my presentation, and I want to thank you for joining me.